All right, so this week is all about sort of the physical properties of real qubits and thinking about things like coherence. So the main readings are Chapter 11 and of Sutter and Chapter 7 of Nielsen and Schwing. I also have assigned the physical implementation of quantum computation by David DiVicenzo. That's the DiVicenzo Criteria, which we'll talk about today, and a retrospective that he wrote in 2018 called Looking Back at the DiVicenzo Criteria, which I think is an interesting companion piece. I have also highlighted an article called Decoherence and the Transition from Quantum to Classical, which is a pretty fun read, and Observation of a Quantum Eraser, and thinking about it in the context of coherence. So lots of fun reading. If you're only able to do a little bit, I'd read the top three. So up till now, we've kind of been thinking a lot about the theory and mathematics and physics applied to our qubit systems, and now we want to think more in an applied and experimental fashion. So the types of qubits we've been talking about so far are logical qubits. They're perfect, and they don't decohere. And when we think about physical qubits, real qubits that are going to be in our quantum computers, there's a lot more considerations that need to be thought about, and they're kind of governed by their coherence time, their ability to hold on to that initial quantum state that they're initialized to, or once they're placed into superposition, or once quantum gates are applied, to hold on to that information. So they're governed by that coherence time. And so it's the goal of researchers and engineers to delay the decay of the physical qubit's quantum state as long as possible. And since the decay is inevitable, the goal of fault-tolerant quantum computation and error corrections is to handle and fix the effects of the qubit's decoherence throughout execution of a quantum circuit. So small errors are going to creep into the state when gates are applied, and after too many gates, you either pass the coherence time and the qubit becomes unreliable, or the errors accumulate to such a degree that it's not of any use anymore, and measurement is too inaccurate to do anything useful. So the two kind of simultaneous goals when constructing a quantum computer are to increase coherence time and reduce errors. All right, so when we think about physical implementations of quantum computation, I think one of the key papers in the field was written by David DiVicenzo, who's a researcher at IBM, where he laid out sort of 5 requirements of the implementation of quantum computation, and they're sort of listed here. So criteria number 1 is a scalable physical system with well-characterized qubits. Number 2 is the ability to initialize the state of the qubits to some simple initial state, like all the qubits in their ground state. The 3rd is long relevant decoherence times, much longer than the gate operation time. The 5th is a universal set of quantum gates. We've talked about one such set, but they might look pretty different than that, or they can. And then finally, a qubit-specific measurement capability. So we want to be able to make our qubit, we want to be able to scale our qubit, we want to be able to initialize our qubits, we want to be able to do something with those qubits, and we want to be able to measure the result. So that's kind of the big goal. So we're going to break down each of these criteria a little bit, and then look at some kind of examples for what this might look like. So when DiVicenzo kind of thought about this idea of creating a scalable physical system, what he realized is that we really need to build a qubit with 2 clearly delineated states. So we need a 0 and a 1. If these states represent energy states, there might be other states nearby that are possible, but we need to be able to isolate these 2 states and control whether we populate one or the other reliably. So the qubit must also be able to move into a superposition of 0 and 1 if those are our two orthogonal states. And those superpositions need to obey the rules that we've laid out over the last couple weeks in terms of amplitudes and probabilities. And as we add more qubits, we have to be able to entangle the qubits either directly, physically, by mixing. So if we're using photons as our qubits, for example, we can pass them through a BBO crystal, and that will lead to entanglement, or indirectly through some sequence of gates in our quantum circuit. And it's not necessary to physically connect every qubit with every other qubit in our quantum computer, and the chip architecture will determine the degree of connectivity so that the overall performance and manufacturability is optimized. So on the left here, we have a connection map for the IBM Q first generation quantum computer. It's a 20 qubit chip. And you can see what the connectivity looks like. So we have parts of the chip where only 2 qubits are connected, and we have parts of the chip where more than 2 qubits are connected. And the layout here is well, it changes with time for sure as people think about new ways to put these things together, but they're developed to decrease errors coming from nearby connected qubits and to prepare for eventual qubit and gate error correction. And then the last sort of thing we need to think about is that through entanglement, we have to be able to see the expected doubling of our vector space for every additional qubit that we add to the system. And we want to do that, we want to realize that doubling of our vector space without doubling the cost. So since 1 qubit is never enough, we want to be able to add sufficient additional qubits so we can do useful quantum calculations, but the cost to add these qubits shouldn't be prohibitive. We wouldn't want the economic cost of or the engineering complexity to be scaling exponentially as we increase the number of qubits. So there needs to be a balance. All right, so for the purposes of computation, it's important to realize that the set of accessible states needs to be finite. So we need our 0 and our 1. So the position of a particle along a one-dimensional line isn't generally a good set of states for computing, even though the particle might be in some well-defined state X. Or even a superposition of different positions along that one-dimensional line. And that's because that position has a continuous range of possibilities, and the Hilbert space that's generated by that continuous set of positions has an infinite size. So it's generally desirable to have some aspect of symmetry dictate the finiteness of the space in order to minimize decoherence. So a great example is using spin. So a spin 1/2 particle lives in a Hilbert space that's spanned by spin up and spin down states. And the spin state can't be anything outside of those two possibilities. And so it's basically our ideal qubit system. So if we're talking about an optical quantum computer, then it's actually like where 2 photonic cavities meet and where 2 photons come together. If we're talking about Josephson junctions, for example, it would be where superconducting qubits can kind of communicate with one another physically. Yeah, there's lots of different ways. The connections can also be done as part of the algorithm. So you can map your circuit, map your program so that qubit 11 talks to qubit 14, but not to qubit 13. All right, so where are we at in terms of numbers of qubits in quantum computers today? This is actually a year out of date, but it's kind of fun to see how many qubits people have put into complete universal quantum computers. So all the ones in the regular yellow color are kind of traditional universal quantum computers, and the ones in the more orange colors are sort of quantum annealers, so not sort of thought of as traditional quantum computers. So we're sort of in the few to tens to maybe up to 100 qubits in these systems. But as maybe a few of you heard, last week there was a big announcement from Atom Computing, and they were the first to exceed 1,000 qubits in a quantum computing setup. So what they have is an array of 35 by 35 trapped ions, and those, or that array of trapped ions is sitting inside of this giant box with all these lasers and things and electronics and all kinds of stuff. And you know, they don't have a quantum computer yet that makes use of all of these qubits, but they're making progress. So this is sort of from their big press release, and they highlight that it's the first time a company has crossed the 1,000 qubit threshold. And when you look at their system, they are marching along the path towards generating a fault-tolerant quantum computer. So their trapped ion qubits do have long coherence times, as we'll talk about. Up to 40 seconds has been measured in some of their systems. They have been able to demonstrate a mid-circuit measurement, so they've been able to measure the quantum state of a specific qubit during computation and detect errors without disturbing other qubits. They've been able to control qubits consistently to reduce the number of errors. They've done some minor error correction. I think that actually all of these three are sort of still in the works, but they're moving towards implementing algorithms and controlling large numbers of physical qubits to make something that looks a lot more like a logical qubit. But again, this is from their press release, and you can kind of read about each of these things on their website or in other news articles. But it's a big deal, and I think they're hopeful to release a quantum computer of this scale sometime next year in 2024. So we'll see. All right, so the next thing is initializing our qubits. So we have to be able to initialize our qubits to a known initial state with very high probability. And this in the field is kind of called high fidelity state preparation. So when you hear that, that means you can initialize your qubits to a known state with a very high probability. And since it's common for algorithms to begin with a qubit in the 0 state, that's a good choice. But if for some reason you can't do that, you can always start with it in the 1 state and then apply an X gate, and that'll bring you to the 0 state. So you only need to be able to reliably access one of your quantum states deterministically, because you can always get to the other by a gate. All right, long decoherence times. We're going to talk a lot more about decoherence and T1, T2, T2 star likely next class. But decoherence in general causes a qubit to move from a desired quantum state to something else. And if too much decoherence happens, the state becomes random and useless. And the qubit has to have a long enough coherence time so that enough quantum gates can be executed to implement an algorithm to do something useful. And if you have long coherence times, but your gate operations take too long to execute, then that's kind of equivalent to having a short coherence time, but with fast gates. So long coherence, fast enough gates, and low error correction is kind of the key to success for quantum computers. So what kinds of physical systems are potentially good candidates? We've talked about many of them here and there throughout the course. But what you want to think about when you're kind of assessing different systems is the length of the longest possible quantum computation given the coherence time of the system and the gate operation times. So that's what's kind of shown in this table. So we have the time for which the system remains quantum mechanically coherent, that's listed here as T sub q, and the time it takes to perform elementary unitary operations or transformations that involve at least 2 qubits, that's listed here as this T op. And then the number of operations is just the dividing those two things. And so you can see that these numbers vary pretty widely. So we really only have 3 distinct kinds of qubits represented in this table. So we have spin, we have sort of atomic levels or electrons in orbitals, and we have photons. So you can see here nuclear spins, for example, have coherence times that range anywhere from 10 to the minus 2 to 10 to the 8th seconds, so quite a range. They have operation times of 10 to the minus 3 to 10 to the minus 6 seconds, so single gate operation times. And so that means that the number of operations that they could potentially do are sort of in the 10 to the 5th to 10 to the 14th range, which is pretty great. If we look at sort of the other extreme, so an electron in a gallium arsenide solid state qubit has a coherence time of 10 to the minus 10 seconds, so not very long. Gate operation times are pretty fast, though, so 10 to the minus 13 seconds, and that combines to give you about 1,000 operations being possible. All right, so a universal set of gates. So you can't build quantum algorithms unless you have a complete enough set of gates. And gates can be created from other more primitive ones. We've seen some examples of that. And the gates that are native to a particular qubit technology might not look like anything that we've seen so far. But so long as they can be composed by some standard collection, you can develop practical algorithms and implement those and deploy those, and that works out fine. So the last criterion listed by DiVicenzo is measurement capability. So we have to reliably be able to force the qubit into one of the 2 orthogonal basis states. So 0 and 1. And the error rate of that process has to be low enough to allow for useful computation. So if we get the wrong measurement answer 50% of the time, all the previous work on executing the circuit is basically lost. So this is called high fidelity readout. If we move the qubit to the plus state, for example, so that's square root of 2 over 2 times 0 plus square root of 2 over 2 times 1. It should measure either 0 or 1 with a 50% probability each. And the same is true for quantum states with known probability amplitudes before measurement. And so in general, a good figure of merit for measurement capability is signal to noise. So this accounts for measurement inefficiencies as well as things like inherent signal strength available from coupling a measurement apparatus to our quantum system. And it's going to look a little bit different for every kind of qubit technology that we consider. So if we consider a qubit state, let's say A0 plus B1, represented by the ground and excited state of a 2-level atom, we might measure that by pumping the excited state and looking for fluorescence. So if our fluorescence instrument indicates that fluorescence has been detected, then the qubit would collapse to the 1 state, and this would happen with a probability of b squared. Otherwise, the fluorescence instrument would detect no signal, and the qubit would collapse to the 0 state. So you can kind of map out the DiVicenzo criteria onto all kinds of qubit systems, and I encourage you guys to do that with the ones that you present. I kind of mentioned to a few of you that I had a group meeting last week where one of my students was introducing this qubit system that was has been studied quite a bit by Kai-Mei Fu's lab, and it's a group 3 donor defect like gallium or indium in a zinc oxide semiconductor. So this introduces a shallow donor level into this wide bandgap semiconductor, and it generates a system that can be a really great qubit. So we can think about, in the absence of a magnetic field, we have a neutral donor. So this is like an N-type dopant in our semiconductor. So we have zinc oxide to start. We replace one zinc, which is in group 2 or 12 of the periodic table, by a gallium, which is in group 13 or 3 of the periodic table. So that adds an extra electron to our system, neutral donor. And then we can photoexcite the system. And that neutral donor can trap an electron hole pair, an exciton. And then when we apply a magnetic field, we get Zeeman splitting of both our neutral donor state and our excited exciton bound state. And so this gives us a mechanism, a lot like what we looked at for NV centers, to selectively initialize either of these two spin states in our Zeeman split ground state. So this is a really great way to map onto the DiVicenzo criteria. So these are well-defined qubits. They can, in principle, be made scalably. We can make lots of them. We have a well-defined two-level system. That's our Zeeman split ground state, so our spin up and spin down electrons. We can initialize each of those states, the 1 and the 0 state, the spin up, spin down state, by optical pumping. We can photoexcite our zinc oxide and selectively get to one place or the other. We can measure what state we're in, and we can reliably, experimentally pump between those two states by using microwaves, because the energy difference between those two Zeeman split levels is in the microwave regime. We can measure the coherence time of these qubits, and they're pretty long. So there's, again, these sort of 3 primary coherence times that we'll talk more about later this week. So we have T1 times in this system are about on the order of 0.1 seconds, so pretty darn long. We have T2 star times that are sort of on the order of 17 nanoseconds, and we have T2 times that are on the order of about 50 microseconds. So all pretty long. And then we can kind of use our universal set of quantum gates to manipulate these qubits. And if you want to read more gory detail about the system and sort of think about how these donor defects in zinc oxide function as qubits, you can read many of Kai-Mei's articles, but this one in particular has a lot of just the basics of these donor defects in zinc oxide. All right, so when we're thinking about coherence, it's often useful to come back to light as, well, a great qubit, and also just a great example to kind of start our discussion. So we know that light has both wave-like and particle-like characteristics. It travels with a known speed of about 300 million meters per second, which is really fast. And when two waves, two photons, take up the same space at the same time, we get superposition. So here's 2 photons. They have very different phases. So one has a pretty long wavelength, and one has a pretty short wavelength. And This leads to, if they're in the same place at the same times, you can get interference. So any point where the waves overlap, their amplitudes, positive or negative, add to give a new combined amplitude. And if both amplitudes have the same sign, we get constructive interference. And if both if the amplitudes have different signs, we get destructive interference. And if the new amplitude is 0, that means we have complete destructive interference. So for a given wave with a repeating period, like we've shown here, we can measure various points along the horizontal from the beginning of the period to the end, and that gives us our phase, which I've kind of marked in the two cases, and that takes on values in radians of 0 to 2 pi. And we can define coherent light by having the same amplitude, the same frequency, and we require that the waves are in phase with one another. So light from a laser is coherent because of the mechanism by which the light is generated. It's generated from spontaneous emission from some material that has been pumped to be in a population inverted state so that all of those excited states relax at the same time. So all of the light comes out, same direction, same wavelength, same properties, all in the same at the same time. But you can also generate coherent light in more simple ways rather than population inversion. So you can take a random light source like an arc lamp or an incandescent light bulb, and you can pass that light through a pinhole aperture, and that makes the light spatially coherent. And then you can pass it through a wavelength filter, and that makes it wavelength coherent. Okay, so the double-slit experiment is one of these classic examples in quantum mechanics that reinforces kind of the interesting properties of light. So if we take a little gun that shoots BBs, and we have a screen that blocks all the pellets except for those aligned with these two slits. If we shoot lots and lots of pellets through, we might allow for some horizontal scattering, but the impact area on the back wall is going to look the same as the shape of the slit, right? So we're going to end up with two kind of bands. But of course, instead of pellets, we can consider photons. And we have our little photon shooting machine, a laser. And so the light coming out of this laser is coherent. And it has some constant wavelength. And when we think about the light as a particle, the photon passes through one slot or the other, but not both. But the photons, of course, also behave like waves. And the light waves interfere with themselves after they pass through the slits. So instead of getting solid bands, like we saw in the sort of pellet case, we get diffraction and strong bands between the slits and weakening bands to each side. And that's because of the constructive and destructive interference that we talked about on the last slide. So you can see this kind of illustrated, the experiment illustrated in this diagram. So we have some directional light source coming through a pinhole. We have an observation screen. If we just pass the light through one slit, we get some distribution of light as it's spread out past our pinhole. If we put it through the other slit, we get some distribution of light coming through that left slit. And if we put the light through both slits at the same time, we get an interference pattern. So the ability of light to sometimes behave like a wave and sometimes behave like a particle is this idea of the wave-particle duality. It's kind of a historical physical model more than it is anything about quantum optics, but it's useful. And Feynman made the kind of classic comment that everything about quantum mechanics could be encapsulated in the double-slit experiment. So in the double-slit experiment, you shoot photons one at a time towards a wall with two narrow slits. And where each photon lands on the second wall is probabilistic. And if we plot where the photons appear on the back wall, some places are very likely and some places are not. So that's not the weird thing. We could justify that happening by some theory where each photon just had some extra degree of freedom, maybe like an RFID tag that we didn't know about, and that determined what way it went. What's weird is that if we think about some interval on the second wall, so if P is the probability that the photon lands in the interval when both slits are open, and P1 is the probability that the photon lands in the interval when only slit 1 is open. And P2 is the probability that the photon lands in that interval when slit 2 is open. You'd think that P equals P1 plus P2, but that is not the case. So the experiment shows us that there's that even places that are never hit when both slits are open, they can sometimes be hit if only one slit is open. And then you can think, okay, well, what if I measure which slit the photon went through? It turns out that doing that changes the measurement into something that makes more sense. It looks more particle-like. And it doesn't have to be a conscious observer doing that measurement. If the information about which slit the photon went through leaks out in any way, the results go back to looking like they would obey these classical probabilities again. So if an observer comes in, how do we make this little eyeball symbol? This, yeah, thank you. Eyeball. If an observer comes in, then everything collapses to classical probabilities. And so there's a famous experiment called the quantum eraser that kind of relates to this. So one version uses polarizers in front of each slit to label the photons, and you get kind of this reversion to classical particle-like behavior. And so this reversion to classical probabilities, when systems are coupled to their environments, when there's a measurement, for example, that's called decoherence. So decoherence is why the usual laws of probability look like they work in everyday life. A cat isn't found in a superposition of alive and dead states because it interacts constantly with its environment. And so those interactions essentially leak information about the cat system out. And quantum superposition is something that happens to particles or groups of particles when they're isolated from their environments. And needing the particles to be isolated is why it's so hard to build a quantum computer. So when we often talk about light and the double-slit experiment, another thing, another kind of example that comes up is thinking about polarization. And we talked a little bit about some fun examples of polarization last Friday. But I figured it would be worth going through one other kind of interesting observation about light before we move forward with talking about coherence in more detail. So let's consider a general quantum state for one qubit in the computational basis. So we have psi equals A0 plus B1. And we're going to pass that qubit through a series of procedures, and we're going to see what comes out the other side. So the first thing we're going to do is pass our qubit through this thing called a one blocker. So I take my qubit, it's in A0 plus B1, I pass it through the one blocker, and with probability A squared, the qubit will emerge on the other side, and it will have state 0. With a complementary probability B squared, the qubit will be completely blocked, and nothing will come through. So goodbye, qubit. So I can also, in a similar way, define my 0 blocker, and same qubit going in, and coming out the other side with probability B squared, I get 1, or I get nothing. And so the final, the sort of final thing to think about is if I compose these two blockers. So I take my initial qubit state, I pass it through the one blocker. If I have anything at that stage, it's a 0. And then I pass it through the 0 blocker, and so after that, I have nothing, right? Nothing is coming through. So the last thing I can think about to modify this system is I can add a twist. So imagine I have a qubit with state psi equals C plus D minus, and I define this plus blocker, which tells me when I pass my superposed qubit through, I get a qubit state with minus, with probability D squared, or I get nothing. And so the question is, if I take my initial qubit state, A0 plus B1, where when I pass it through a 1 blocker and then a 0 blocker, I get out nothing. Now, if I pass it through a 1 blocker and then a plus blocker and then a 0 blocker, what do I get? And so to answer this question, it's useful to remember that our plus states and our 0 and 1 states are related to one another, based on what we discussed with the block sphere. So after the 1 blocker, I'm going to have 0 with probability A squared, if anything, and assume something is there, then this is also equal to square root of 2 over 2 times 1 plus minus. And now I can run that state through my plus blocker, and with probability 0.5, I'm going to get out a minus or nothing. And if anything comes through, I'm now going to pass it through the 0 blocker. And so out the other side, with probability 0.5, I'm going to get a qubit in the 1 state. And so in the case where we used only the 1 and the 0 blocker, no qubit made it through. But oddly enough, now when we inserted the plus blocker, between them, the qubit in the initial state A0 plus B1 made it through with the probability A squared times 0.5 times 0.5, which is A squared divided by 4. So that's pretty weird. And that's the math behind the classic 3-filter polarization experiment. So when you think about a photon as a wave, the wave travels in one direction, but the peaks and crests of the wave are perpendicular to that direction. So if we consider a string on a musical instrument, if you pluck it by pulling straight up and releasing, the wave will rise and fall vertically, or we'll call it up. And if you pluck it directly on its side, the wave will rise and fall from left to right or horizontally. We'll call that right. So a photon in a two-state quantum system, we can use the up and horizontal state as our orthonormal basis. And rather than thinking about a qubit making it through the 1 and 0 blocker scenario, we can consider a photon passing through or being absorbed by a polarization filter. And so we start with the photon in our general state, A up plus B horizontal. And so a vertical polarization filter will absorb the photon with probability A squared and pass it through with probability B squared. And similarly, a horizontal polarization filter will absorb the photon with probability B squared and pass it through with probability A squared. And so up filter followed by a horizontal filter will absorb all the photons. Nothing comes through, just like our 1 and 0 blocker system. So now we can add a middle filter. So we're going to call it a diagonal filter. It's in the basis kind of up diagonal and down diagonal. That's our orthogonal basis for that filter. And so when we put that guy in the middle, all of a sudden our probability for a photon reaching the other side is A squared divided by 4. So this experiment was first proposed in a 1930 textbook by Paul Dirac. And what's cool about it is it demonstrates quantum states, superposition, alternative basis kits, and you can do modifications of this experiment that lead to really weird results that are related to coherence of photons.